रोहित जी, डॉक्टर प्रगति श्रीवास्तव को होस्ट बनाइए। नंदिनी, आप सुन पा रहे हैं मुझे? नंदिनी जी,
हाँ जी सर।
आई थिंक 210 प्लस कैंडिडेट्स ने यहाँ ज्वाइन किया है। यूट्यूब पे भी 200 प्लस कैंडिडेट्स ने ज्वाइन किया है। तो मोर और लेस 450 प्लस पार्टिसिपेंट्स आ गए हैं। 450 प्लस। तो विद इन 1 मिनट हम स्टार्ट करेंगे। एक फाइनल रिमाइंडर आप फैकल्टी और पार्टिसिपेंट्स के ग्रुप में डाल दीजिए। ठीक है? 500 पार्टिसिपेंट्स जैसे ही आ जाएगा हम स्टार्ट कर देंगे। विद इन 1 मिनट आप मैसेज करिए।
डाल दिया सर।
ठीक है।
सर, एम आई ऑडिबल एंड विजिबल क्लियरली?
यस यस यस, अब आप स्टार्ट करिए प्लीज।
So, good evening, everyone. A very warm and heartfelt welcome to all the participants joining us for the day 6 of International Agriculture Workshop Come Training Marti 2025. This side, Nandini Sharma from AgriMeet Foundation Bharat, and Marti 2025 is proudly organized by AgriMeet Foundation Bharat along with our esteemed national and international knowledge partners. So, before we begin, I want to humbly remind everyone why Marti 2025 is special for all of us. This 10-day international program is designed not just as training but as a visionary movement dedicated to transforming Indian soils through scientific innovation, global thinking, and sustainable practices. Every day of this workshop opens new doors of learning from soil health and nutrient management to precision agriculture, digital diagnostics, climate smart strategies, and AI enabled tools. The essence of Marti 2025 is to empower every participant to become a future ready scientist, researcher, and agricultural leader. So, it is my absolute honor and a moment of true privilege to welcome a towering pillar of Indian agriculture research, Dr. Kotha Sami Reddy Sarji, Director ICR, National Institute of Abiotic Stress Management, Pune. Sir, your presence today elevates day 6 of Marti 2025. We are deeply grateful and genuinely humbled to have a scientist of your status, experience, and global recognition among us. Your journey is not just inspiring, it is a benchmark for excellence in agricultural sciences. Sir is a renowned scientist with an extraordinary career dedicated to soil science, resource management, climate resilience, and abiotic stress management. Born in Telangana's Karimnagar's district, Sir went to pursue BSc Agri, MSc Soil Science, and a later PhD from IARI New Delhi, one of the most prestigious institutions in the country. Sir has served in some of the India's most important scientific establishments, scientific assistant at National Remote Sensing Agency, Hyderabad, scientist and senior scientist at Indian Institute of Soil Science, Bhopal, principal scientist and head at ICR Crida, Hyderabad, director ICR Crida, Hyderabad, and currently the highly respected director ICR NISM Pune. With 400 scientific publications, including 150 research paper, articles, 24 books and 25 book chapters, Sir has contributed immensely to the global soil and climate research. His awards and recognitions are equally remarkable. He has been awarded with Dhiru Morarji Memorial Award, ISS Young Scientist Award, Golden Jubilee Commemoration Award of ISSS, FAI Awards, Fellow of NAS and ISS. Sir has represented India across the world from Australia, Philippines, Kenya, Poland, Thailand, Singapore, Malaysia to Hong Kong, presenting research and advancing global agriculture. Sir, it is truly an honor to have you with us today. Your presence adds immense value, grace, and inspiration to Marti 2025. We are deeply grateful that you accepted our invitation. With utmost respect, we now request you to kindly begin your session. Over to you. The session is yours, sir. Thank you so much.
Actually, I will share my presentation, okay?
Yes, sir. Yes.
Hello.
Your screen is there, sir. Like,
Not at
please open. No, it's
Not-
there. Please open the PPT, sir. Please open the PPT. Yes.
No,
Sharing is there. Your screen is visible, sir.
no,
Just
visible.
minimize.
It is visible.
Yeah, visible. Yes, visible.
No,
Yeah, the PPT. Yeah, click on, yeah. Go on PPT mode, sir.
no. Is it okay now?
Yeah, sir.
Yes, sir. Done, sir. Done, sir.
That first slide is visible.
Yes, sir. Slides are moving also. That.
Okay. Yeah. Dr. Ankur Sharma and all his colleagues, and most importantly, 213 participants. As of now, actually, according to this,
287 plus, sir.
yeah, 287 participants.
ये
And
जूम पे है,
also-
यूट्यूब पे भी काफी ने किया है. 200 प्लस जूम पे, उस पे भी है, यूट्यूब पे.
Okay, very good. More than 200 in YouTube.
हाँ, 500 के लगभग में है, सर. 500.
Yeah. Good evening to all of you. And of course, this is a little bit different, maybe lecture for all of you, because it's not directly related to the soil fertility, soil nutrient management, but it is still broader. Because I am the director of National Institute of Abiotic Stress Management. And one of the school we are having is the School of Edaphic Stress Management. Edaphic or the soil stress management. So basically, actually, I will talk on this edaphic stress management for sustainable agriculture under changing climate. This is the content what I am going to cover. So all of you know, edaphic stresses are the soil stresses, because students, particularly edaphology, all of you know that is the study of soils in relation to plant growth is edaphology. And soil stresses are edaphic stresses, that are the stresses of the soil, are the constraints of the soil that are going to adversely affect the crop growth and yield. That is the thing. And the only thing under changing climate, what happens is not only soil stresses, but other associated stresses will be there. All of you know atmospheric stresses, water stresses, as well as the soil stresses. If you go to any farmer field, farmer will face in the field many stresses together. That may be the biotic stresses, abiotic stresses. Among the abiotic stresses, it may be a water stress, it may be the drought stress, it may be a soil stress, like that. So I want to actually highlight how to manage when the stresses occur frequently in multiple means in different stresses occur together, multiple stresses, that how to manage them, and what are the stresses of the soil, are the edaphic stresses with the interactions with the other stresses, atmospheric stresses as well as the water stresses, and what would be their impact if they occur together, what would be the impact on the crop yield reduction, that is, and how to manage them. Briefly, I will cover. Actually, this is the basic coverage of my topic for next almost 1 hour. And all of you know, stress means it is the environmental condition that interfere with the plant growth process or the plant functions. And among these stresses, the abiotic stresses are very, very important, along with the biotic stresses. Abiotic stresses, they are the negative physical or the chemical environment that poses significant challenge to maintain delicate balance among soil, plant, climate in agriculture. And these are the abiotic constraints, that is the physical, chemical, environmental constraints, but mostly that are going to affect the adversely the plant growth and also cause reduction in the crop yield. And in the literature, if we see, it is found that abiotic stresses cause yield reduction up to 50%. That mostly it varies from the 30 to 50%. The maximum what we found is the most of the median figure is that 50% reduction will be there. On an average, literature shows. And this loss will increase by 10 to 40% in India by 2080 to 2100 if we don't adapt any adaptation mitigation strategies to manage the climate. Actually, this is a very, very important. And the nearly 90% of our soils are the cultivable lands. They are affected by one or other abiotic stresses. That is very, very important. Already told, edaphic stress means the soil conditions that reduce the plant fitness is a primary pervasive constraint to plant productivity in terrestrial ecosystems. Actually, indirectly, it is the soil constant that affects the plant growth and yield adversely. So already told, under the field conditions that most terrestrial plants experience a combination of multiple abiotic stresses concurrently. Actually, this is very, very important, that this is the actually focus point of this lecture. And if you come to the edaphic stresses, all of you know, they are generally categorized into three. One is the internal soil process, internal edaphic stresses, external edaphic stresses, anthropic edaphic stresses. Internal edaphic stresses means that are the stresses that come from the actually due to the inherent properties of soil, like the nutrient deficiencies, excess soluble salts, salinity, alkalinity, low base saturation. All of these come from the inherent properties of the soil, like the others are there, metal, toxicity, calcareous, whatever it may be. I don't want to read. All of you know that even low and high organic matter ecosystems, that is a low soil resilience, natural soil degradation, all these are the because that happen mostly because of the properties of the native, that is the parent material and other mineral contents of the native soils. And external stresses, external edaphic stresses, that are mostly because of the external factors, that is the environmental factors. They are the climatic controlled factors like extreme climate regimes, high and low temperature, water logging, nutrient leaching, global warming, insufficient length of growing season, etc. And sometimes pests and diseases, high termite population, they also causes sometimes edaphic stresses. And all other climatic parameters like the El Nino storms, cyclones, floods, water logging, droughts, landslides, all these are the examples of the external factors that cause edaphic stresses. They are the external edaphic stresses. And anthropic stresses, they are the mostly because of the human activity. And it is very, very difficult. Sometimes some of the stresses may be both because of the anthropic activities also, human activities also, and sometimes external these conditions also. It is very, very difficult to say. But in broadly, we categorize these edaphic stresses into these three categories. And this all of you know, and in India, vertisols, inseptisols, entisols, iridisols, alpisols, actually these 4 or 5 orders, mostly they constitute nearly 85% of the soils. And of course, some other soils are there, but where in each, I don't want to go into deep of these constraints or the edaphic stresses that are associated with the different soil orders. For example, vertisol, if we see, we all of us know, they are very, very difficult to work, because if too little bit high moisture means it is very difficult to enter into the field, and even little bit less moisture means it may sometimes it is very difficult to work with them. So that is a very hard, that type of the condition. That is why they are called as the swell string soils also. And if we see some of the constraints very hard when dry, very plastic, sticky. I don't want to read. All of you know, and low infiltration rate, poor internal drainage, salinity, alkalinity, and deficiency of the micronutrients. Even black soils also, they are sometimes deficient in soil organic carbon. Even many vertisol soils are there which are low in organic carbon, below the 0.5%, like that. And inseptisols are, there are several constraints already I have listed. You can read afterwards also. Entisols or iridisols, and also the alpisols. Alpisols, like the red soils, particularly, the most common problem is the surface crusting and sealing, low water retention, low fertility, acidic conditions, high erosivity due to undulating or the rolling topography. Only I have listed few, actually major ones, but you may find many other also. Wherever almost all our soils are deficient in nitrogen, like that. Many other edaphic stresses are there, but only few which are specific to that particular soil order I have listed here. And if we see this Friedrich et al. Globally, he has identified nearly 25 edaphic stresses, major stresses that are being faced by different soil groups of the world. And in this, he categorized these 25 edaphic stresses into the 9 groups, 9 classes. That is the 8th and 9th class means 9th classes. They will have 85% risk of these due to the edaphic stresses. Means they are highly high intensity. They will having the more intensity of the edaphic stresses. And like sixth and seventh means 60 to 70 to 80%. Like fifth means 40 to 50%. And first class means that is the better, means best without any major edaphic stress. But they are very, very less. And they also found that the major edaphic stress is the faced by global soils is the continuous moisture stress. Of course, moisture stress may be lack of irrigation facilities or the lack of rains or the drought or the dry spells, but that will have so many effects. All of you know that nutrient availability, everything, microbial activity in the soil, everything depends upon the moisture content. So the soil moisture content is the major constant that was observed among the edaphic stresses all over the world, and it is also true in India also. India also, it is the major constant. And of course, order I have written 1, 2, 3, 4 like that. If we can go through others followed by the soil fertility constants like that, these are the major constants that are happening. And if it is the physical constants in India, about 90 million hectares of the soils, they are having one or other physical constant. For example, shallow depth. Soil depth is a edaphic stress over 26.4 million hectares. Like soil hardening is a major stress in 21.57 million hectares. Like that, high permeability, subsurface hard pan, surface crusting, temporary waterlogging. All these, if we put together, we have about 90 million hectares of soils where they are facing constants or the stresses due to the physical properties, poor physical properties of the soils. And if we move to the available nutrient status, soil fertility, if we see this soil fertility maps prepared by IISc Bhopal, that is by Dr. Y. Muralidharan et al. In 2011, you see almost almost 57 plus 93% of soils are low to medium in available N, and 51% of soils are low in available P, 40% are medium in available P. And potassium, of course, is 9% soils are low, and 42% soils are medium, and 49% soils are high. Actually, particularly potassium is concerned, wherever red soil areas are there, laterite soils, red soils, particularly South India, Eastern India, and some parts of the acid soils belt, they are having the mostly actually deficiency of the potassium. Otherwise, our wetty black soils and the alluvial soils, they are medium to high in available P. And recently published that micronutrient soil micronutrient maps. If you see that that were published by the Shukla et al. 2021, again from the IISc Bhopal, according to them, 58.6% of soils are low in available sulfur, 51% are low in available zinc, 45% of soils are deficient in available boron, like that iron, copper, manganese, they are also about 11 to 19% of soils are low in iron, copper, manganese. The important is that, for example, 9.3% of our soils are deficient in both sulfur and zinc together. Just I have worked out the combinations to highlight the multiple nutrient deficiencies. Like that, 8.7% of soils are deficient in zinc plus boron. 7% soils are deficient in sulfur plus boron. Like that, if you come to this, the zinc, iron, copper, manganese, all four nutrients are deficient in about 0.3% of soils. Like that, sulfur and zinc boron, they are deficient in 2.6% of soils. Sulfur plus zinc plus iron, they are deficient in 1.7% of soils. What I mean to say is that, of course, nitrogen is deficient, that no need to tell, more than 90% of the soils. P is also deficient. And if we see these combinations, it highlights that if managing one nutrient is not important, if multiple nutrient deficiencies are there, we have to manage them together. Then only we will get the our expected benefits from the soil fertility management. For example, these are the, actually, apart from that, they are the older maps that are seen, but what we did also at our institute, we have collected the nearly 16 crore soil health care card data that is available with the Ministry of Agriculture and Farmers Welfare, Government of India, and they have permitted us. And from that also, using that 16 crore soil health data, using nutrient index methodology, we have also developed soil fertility maps. This is, for example, the organic carbon, according to that maps, nearly 54.5% of soils are low in organic carbon, 37.7% are low in medium, and 7.5% soils are high in organic carbon. Like that, nitrogen also is shown. 53% are low, 47% are medium, and about 1.1 to 2% are high. More or less, they are similar to the what is that? Only little bit differences are there, but otherwise, more or less similar to the Muralidharan. But most of the soils, actually, because of certain reasons, they are low organic carbon and these. And if we come to the available nitrogen, available phosphorus, available potassium, if we see particularly available phosphorus and available potassium, if we see that as compared to earlier maps that were developed in 2011, the percent of soils that are in medium is high. Actually, around 51% soils are medium in available P, and around 9% soils are also available high in available phosphorus. This medium to high available P soils day by day increasing, and potassium is also more or less to the similar to earlier maps that were generated. And here also, actually, I have worked out these. These are the, of course, again, the similar type of the soil healthcare data generated soil maps for the zinc, available sulfur, available boron. Here also, if see that Shukla map that about 51% soils were deficient in available zinc. But here that is coming only 49% are medium and 36% are high. That means actually continuous application of the zinc, like the nitrogen, phosphorus, and other potassium fertilizers, some low soils also became now medium. Actually, this is one of the important according to this soil health card data, but a little bit differences are there. Otherwise, most of the cases trend is same. And here actually again nutrient interactions, like I have shown earlier table, here also I have worked out. For example, if we see the first map, multi-nutrient deficient districts, nitrogen and phosphorus both are together deficient in about 33% of soils. And NPK, all the three nutrients are deficient in 14.5% of soils, like that. Nitrogen, phosphorus, sulfur, they are deficient in 5% of soils. Like if we see nitrogen, potassium, nitrogen, phosphorus, potassium, sulfur, zinc, boron, they are deficient in nearly 1 to 2% of the soils. So what I mean to say is many soils, they are deficient in multiple multi-nutrients, like not only the major nutrients, but also micronutrients also deficient. For example, like that here also, medium, if you see medium, that NPK, about 1.3% of soils are medium NPK. Like that, if we come to the 3.9% of soils are medium in NNP. Generally, we recommend the fertilizers at recommended rates and more than recommended rates to the soils which are low to medium in different available nutrients. So this is actually, what I want to say is that wherever the multiple nutrient deficiencies are there, we should manage them together. And if degraded wastelands, if this is also in India, we are having almost 104.2 million hectares of degraded lands. That too agricultural lands cultivable. If we include the forest lands also, that degraded lands, that will come to the 120.7 million hectares. Of course, this figure is recently revised. That is about 1.10. This 104.2 million hectares has come down to nearly 80 million hectares of the degraded land. But that map is not yet finalized. But once finalized, this table may be revised. And among this degradation process, also all of water erosion is the major thing, and followed by the wind erosion. Followed by, of course, chemical degradation like the salt-affected soils, acid soils, and like that. And this is the map of the acid soils of India. If we see, nearly 30 million hectares of soils in India are strongly moderating to strongly acidic. That means they are having the pH below 5.5. And globally also it is a major threat. But whenever acid soils are there, they also associate with availability, severe deficiency of availability. Even 70% of acid soils globally, which are having the pH less than 5.5, low availability. Average phosphorus content of the availability content of these soils is only 9 milligram per kg. Actually, this is the recent reference. And these acid soils, because actually one is how that affect the soil crop growth is that one is the nutrient balances, second is the toxicity of iron and aluminum, third is it also affect the root growth, And fourth is many soils, they are also deficient in the available boron. So actually this is not only their acidity creates a problem, but also available phosphorus, available boron, and iron and aluminum toxicity, and other nutrient imbalance also that are the major eutrophic stresses present in the acid soil areas. And of course, this is salt effect soils. I don't want to go much into this because a lot of work has been done at CESRI Karnal. According to them, now 6.73 million hectare soils are under problem soils, which is the saline soils, alkali, or the saline alkali soils. And 2.96 million hectares are saline soils, 3.77 million hectares are the alkali soils. And this increasing frequency of the climate change, particularly, that is causing like the climate change events or the extreme events like the droughts, floods, cyclone, excess rainfall, etc. They are increasing, causing the soil salinity in dryland areas also. And that is the dryland salinity we call. And secondary salinization in irrigated areas, as well as the saline in coastal areas due to soil water intrusion. So all the three major three groups of our three areas or regions, they are facing the salinity problem because of salinity and alkalinity problem because of the increasing frequency of the climate change aberrations. And this particularly in India, all of you know that around 70 million hectares, now 49 to 50% of soils are rain-fed. Even after so much development, irrigation, wide spreading of the irrigation facilities, and every year government is spending a lot of money in developing irrigation facilities. But even then, as of now, also about 49% of soil, our cultivable land is under rain-fed conditions. Of course, recently it has come down to 50%. Otherwise, earlier we used to tell that 51-52% of soils are rain-fed soils, but now it is around the 49 to 50% of soils are rain-fed. But these rain-fed soils, all of you know that they are not only thirsty but also hungry, and they all these like other irrigated soil areas. The work done at CRIDA showed that all our drylands are the rain-fed areas, rain-fed soils of different regions. They are deficient in 2 or more nutrients. That's the major nutrients as well as the micronutrients. Sometimes, of course, sulfur and calcium deficiency is also spread. Calcium particularly deficient in case of the acid soil areas as well as the alkali soil areas. Red soil areas. And of course, one of the important the climate change is that increasing heat waves in India. If we see this all over that red marks, that red triangle, fully filled red triangle, that the probability of this occurrence of the heat stress is increasing. So whenever heat stress is increasing, it is definitely affect the soil properties, soil fertility, soil physical property, for example, porosity, aggregate stability, wettability, water repellency, water fluxes, or the soil chemical properties like the quantity and quality of the organic nutrient, organic as well as the inorganic nutrient fractions, organic matter itself, and biological activity. All of you know that where temperature exceeds, and whenever that high heat stress is there, high temperature is there, that causes degradation of the soil organic matter and loss of soil organic matter. That's why most of our tropical and arid, semi-arid soils are low in available carbon. And soil moisture stress, of course, that is no need to tell that heat stress that causes the loss of the soil moisture, which is ultimately leads to the low moisture availability and this drought, soil drought. And it is found that on an average, 25% of the less soil biological activity, and that is because of the heat stress. And that also adversely affect the nutrient cycling. This actually I have found some average figure that because of the heat stress, our biological activity will be reduced by 25%. Actually, that all of you know that also affects the transformations and availability of the nutrients in the soils. Like that, cold stress is there. Cold stress also affects particularly it affects adversely the microbial activity in the soil, reduces the microbial activity that in turn affects the organic matter and nitrogen, sulfur, and phosphorus, which are organic fractions also important, the nutrients, wherever they are important, the transformations of that organic fractions into the inorganic fractions are available forms that is going to be affected adversely. So these are the weather, some climate change variables that are going to affect our causes soil edaphic stresses. And areas prone to the waterlogging. All of waterlogging means wherever the waterlogging is there, that causes the this flooding and waterlogging. Again, it affects the nutrient availability. One most important is that nitrogen loss due to the denitrification in particularly our anaerobic soils or the waterlogged soils. In India, about 34.8 million hectares of cultivable lands, they are prone to floods and waterlogging. So intense floods that release and redistribute salts from geological substances would put pressure on more areas at risk of soil salinization. Again, this also causes, for example, if saline waters are there or salinity is there in the deeper horizons of the soil, when the excess water is there, that will come onto the surface. And when the water get evaporated, they accumulate in the soil surface. So that also causes the actually this salinization. So this that is why actually the important thing is that where then the edaphic stresses and other stresses like the whatever I mentioned, like the heat stress, drought stress, all these stresses, they are occurring together. So it is very essential to understand the interaction between the edaphic stresses as well as the other stresses. So the interaction type in the literature, if we found particularly, there are 5 types of the interactions between edaphic stresses and with the other stresses. For example, first is the dominance of the one stress over others. For example, here, if the drought stress is there, nutrient deficiency stress is there. That drought stress actually that dominates. But nutrient stress is also important, that but intensity may be the less. So here, if this type of that is there, first we should manage the drought, followed by the nutrients. So like that, actually interaction that helps. Another neutral are the additive interaction, where when 2 or more stresses are occurring together, their total effect is more than the total of the individual effects. That is the additive. Okay. And mitigating interactions is there. Mitigating interactions, sometimes what happens, presence of the one stress that mitigate the other stress. For example, here it is a drought is there. Because of the drought, crop growth will be less, nutrient growth will be less, overall crop growth and yield will be less. So that requires the less nitrogen and other nutrients as compared to the fully irrigated of the same crop. So thereby, whenever that growth is reduced, that the demand for the nutrients is less. So even the soil, sometimes the soils are medium or low in our nutrients. If we apply some minimum doses also, we may get, of course, less yields, but that helps in mitigation process of the nutrient deficiencies like that. And the potentiating interactions are there. Potentiating interaction is the most important interaction. The presence of the one stress increases the adverse effect or the intensity of the other stress. So the total effect will be, combined effect will be higher than the individual effects. This is the one potentiating interaction effect. And this is, of course, reverse. Additive means that the total almost total is equal to the total, but potentiating means is higher than the additive effect. And dynamic equilibrium, this is the one kind of the interaction with the edaphic stresses with the other stresses. Here, what happens when 2 stresses are happening together, plant actually, because of the our management or because of the inherent properties of the plant, tolerance properties of the plant, that first adjust to the first stress. Subsequently, it's also mitigate the other stress. So, but this type of the situations very, very less happen, practically. So overall, I want to say this: when stresses are occurring together, edaphic stresses and other stresses, they are occurring together, we have to understand their interactions, which depends upon the nature and severity of the stress, type, and response. And we should, after understanding, we should develop these strategies for managing them together. And this is the one slide actually I'm showing that global climate change interaction effects on the edaphic stresses. These are the major global climate change variables. Elevated temperature, carbon dioxide, heat, drought, soil degradation, flooding, and the UV radiation. If we all of them, all will have negative, means potentiate or the increasing the edaphic stress intensity, except elevated carbon dioxide. This elevated carbon dioxide, this one, the impact of the potential edaphic stress interactions crops would be severe than their additive effects. Actually, whenever this climate change variable except carbon dioxide also I will show how that effect depends upon the properties of the soil. But this will have some beneficial effect, but all other variables, they will have the potentiating effect on the edaphic stresses. Means the adverse effect of the edaphic stresses increase in the presence of the our climate change variables or extreme events. For example, if we see some of the examples I have shown here, for heat stress is there individually as compared to the heat stress alone, but heat plus nutrient deficiencies occurring together that causes 14 to 27% higher reduction in the yield. Actually, that is why this is called the potentiating effect. For example, several examples I have taken from the literature. For example, cold stress is there. It may cause loss of crop yield by 12 to 22%, but cold plus salinity stress is together that causes a higher crop yield reduction. For example, 15 to 34% in the crop growth or the yield. Like that, cold plus nutrient deficiency 16 to 28%, cold plus flooding 18 to 36%, because I took ranges from the literature and I put in the form of the literature these ranges. Like that, many drought stresses are there, and what are the effect of drought when associated with the soil stresses like the salinity or the nutrient deficiencies, like that I have given afterwards. Also, you can go through them. This is a very important. I was mentioning about the elevated carbon dioxide. Actually, if you see one of the work, this graph, that work done at CREDA by Vanaja et al. Of course, I was also part of that research. In groundnut, as compared to ambient temperature, elevated temperature, that is by 3 degrees centigrade, definitely reduced the yield, CD yield of the groundnut in all the varieties like we have tried. For example, Narayani, Dharani, K6, K9. But elevated carbon dioxide is also there along with the elevated temperature. The loss caused by elevated temperature as compared to ambient temperature is somewhat compensated. Means the yield loss as compared to ambient temperature in case of the elevated temperature is more than the loss in the elevated than the loss because of the together elevated temperature, elevated carbon dioxide. Actually, that little bit, but overall the reduction in the yield because of the elevated temperature plus elevated carbon dioxide is less than the ambient temperature. Ambient temperatures, if we compare, both are less, but somewhat this elevated carbon dioxide somewhat compensated when it associated with the elevated temperature. This is there. But globally, if we see the meta-analysis of the research studies or the papers published, they did this Node et al. Very good paper. What they found is that the benefit out of the 10 soil orders, means different crops grown in different 10 soil orders, 10 different soil types, that carbon dioxide beneficial effect was found only in 2 soil orders. And in 8 soil orders, which almost account for 83% of world soils, they did not find that beneficial effect of the elevated carbon dioxide, whatever I told in the example with the groundnut. So this is a very, very important. That means the beneficial effect of the carbon dioxide also may vary from region to region, crop to crop, as well as the soil to soil, depending upon its properties and the other things. They also studied actually this occurrence of the more and more stresses, edaphic stresses, as well as the climatic stresses. What is the effect on the soil ecosystem services? What they did is actually they found is that with increasing the number of the stresses, there will be a decrease in the soil ecosystem services, and also the severity, with increasing the severity from the 25% to the 75% in the stress level, there is a drastic reduction in the soil ecosystem services. That is there. So next is, of course, another thing, important thing is that this is very, very important slide, particularly for those young scientists, those who are working in the crop modeling, prediction modeling. For them, this is very, very important. Actually, earlier models we know, linear models. Very famous model is the, of course, first model, that is the Liebig's law, and the very, very, very oldest. Based on Liebig's law, of course, so much development has happened. So many models people have developed now. That is the other thing. Two models like the Liebig's law, another is the multi-limitation hypothesis. This is also one of the law, like the Liebig's law. Both otherwise they are very good models, but what they found is that if it's the literature, whenever there are the multiple nutrient deficiencies are there, or the multiple stresses are there, these models, they are not able to predict the impact of the abiotic stress in the presence of the other abiotic stresses on the crop yields or the crop growth. Actually, that is it is around the only 21 to 30% of the cases when multiple stresses are there, these models have been working. But in what we call the 70 to 80% of the cases, both models are not working. That's why nowadays, actually, all of us know, because of the climate change and whatever the pressure that are there on the soils, when we are having the multiple stresses more than two together, there is a need to develop a hybrid models, which may combine mechanistic models as well as the data-driven models using the modern tools like the machine learning and other IT tools. So in this, actually, there is a lot of potential to work. The predicting models need to develop for assessing the impact of stresses in the presence of the other stresses in multiple stressed regions, the crops or the ecosystems. Actually, this type of work now we should do. Of course, managing edaphic stress interaction for sustainable agriculture, all of know coping strategy. First, no doubt, whether it's a soil scientist or agronomist, we must realize the first step that we should develop the multiple stress tolerant crops. Of course, now climate resilient crops are there. Every varieties are crops and crop varieties. And that is the first. We have to select a multiple stress tolerant crop or the crop variety. This is the first step. And second, of course, we should go for the sustainable soil management technologies. Sustainable soil management technology means generally it is not only meeting the crop nutrient demand, but it should also enhance the adaptation capacity of the soil to the adverse conditions or the adverse stresses, that may be the climate stress or the soil stress. And in this particular, very important, the sustainable soil management practice, whenever that improves soil organic matter content and improves the soil structure, then that helps in the soil water storage capacity. Thereby it helps in overcoming most of the stresses, like even not only soil stresses, but the drought stresses and other kind of stresses. So this type of the sustainable soil management technologies we should adopt along with the varieties. Not only the just nutrient management, but wherever that we need, we should go for the sustainable soil management practices which can improve. For example, and of course, the combination of these technologies is very, very important to manage the multiple abiotic stresses. And if we see this this slide, and soil properties, they are the soil properties given: improving soil water storage, soil erosion, controlling soil erosion, soil carbon sequestration enhancement, or a soil structure. These are the properties of the soils which can mitigate, adapt, and enhance the resilience of the soils. So whatever the management practice, sustainable soil management practice, we should select, and so we should improve some of these properties, particularly soil water storage, organic matter content, controlling the soil erosion, and increasing the ecosystem services, like that. So these are for managing these, improving these properties and enhancing the adaptation capacity of the soils. These are some of all of actually no need to tell, like the technologies like the conservation agriculture, or the soil test-based integrated nutrient management. It's not only the nutrient application of the fertilizers, but it's the integration with the manures or the biofertilizers or the other soil amendments like that. Tank silt application, particularly in red soil areas. Resource conservation technologies, organic farming, biochar application in alpha soils, and the in situ, ex situ soil and water conservation measures, agroforestry, or the regenerative agriculture or biodynamic farming or natural farming. Some of these are the technologies I have listed here, which are considered as the sustainable soil management practices. And another is actually a lot of work has been done. Actually, if we see the NIASM, our website also, we have compared this multiple stress tolerant crop varieties in different crops, that are horticulture crops as well as agriculture crops, and that compiled book also placed on the website. You can refer. But what I found, even from my crop improvement scientists, breeders and physiology scientists also, a lot of work has been done in India. But very less work has been done on root traits. Actually, it is very difficult to do work. That's why most of our breeders and the crop improvement scientists, they mostly engaged in other trades, but root trades literature is very, very less in India. And particularly if we see this, for example, a diagram is given, particularly maize and the common bean. If we have the deep root system, means that can take the nitrogen and the other nutrients as well as the water from the subsoil areas. And if suppose they are having the root spread in the surface soils, that the topsoil foraging, that can take up the nutrients from the topsoil. If the breeders should develop a variety which is having the together combination of these two, that is the deep roots along with the good volume density, volume of the roots in surface soil also, that can capture both water nutrients from the surface, also subsurface soils. So that can enhance the tolerance of the crops to drought or the soil moisture stress during the dry spells. So this type of the work actually we should need to do in India. Like good work has been done on this root traits, in particularly in countries like the Israel. And of course, these are some of the examples I have shown. This publication is available on our NIASM website. And this is one of the technology that is developed by our institute. Actually, all of you, particularly I have selected this slide. Why? Because I want to highlight one point. Actually, NIASM Baramati was given this 150 acres land. Basically, it's the hillock land. It is the basaltic rocky terrain. Basically, there was no crop, no cultivation before our giving to our institute. So what I only think is so many steps by doing, like the ripping, chaining of the rocky surface, blasting, and also separation of the stones and pulverization of the stone, then application of the organic material like the spent wash. After doing so many steps and pulverization, and even some of the blocks mixing of the native muram, pulverized soil with the our black soil. This now converted completely this basaltic rocky terrain into our very beautiful cultivable land. Now we are conducting experiments and all other. You can see both pictures are there, 2009 original site as well as 2022 after the bringing them into the cultivation. So this technology became very, very popular in Maharashtra. Even farmers also, they are scrapping their lands. They are bringing the wastelands into the cultivation, particularly this basaltic rocky terrain. Rocky soils, shallow soils into the cultivation, and these are we found very suitable for the our horticulture crops particularly. So this is the first contribution of our NIASM Baramati by our scientists. And in India, we are having around 26 million hectares of the rocky degraded land. At least 50% of that land can be transformed into cultivation by following this technology. The only thing is that there should be a water availability. And this is also there, particularly all of this soya bean, in particular Madhya Pradesh, that faces the problem of waterlogging as well as the multi-nutrient deficiencies. Soils, they are like waterlogging problem, along with they are deficient in particularly nitrogen, phosphorus, sulfur, zinc, at least deficient in the four nutrients. So what we did there, that along with this BBF, means broadbed furrow planting soya bean, we also followed this balanced fertilization or the integrated nutrient management together along with the BBF. The yields almost have gone doubled. So here actually 38%, 46%, 48% increase is there on different farmers' fields because of this combination of the technology BBF along with the nutrient management, balanced nutrient management. Like this, actually, we should, whenever the multiple stresses are there, we should go for the combination of different technologies. Of course, variety is also important. Like conservation agriculture, all of you know, conservation agriculture is one of the best sustainable soil management practice. Only thing is that there is a need to packaging this different components of the conservation agriculture, and we should implement all these as a package on the farmer fields. For example, sometimes we do not, we recommend, we ask them to farmer that apply the residues, but if suitable farm implement is not there, they cannot do. So what we did in sugarcane, we developed this all together for a suitable farm implement, nutrient and water management, residue management, soil moisture management, weed management, pest management. All we have developed this technology and put them into a package. And now many farmers in Maharashtra, they are actually purchasing this whatever ours we commercialized also. We have applied for the commercialization to our AgriInnovate, this multifunctional ratoon drill, which we developed for encouraging this conservation agriculture or the residue management incorporation in sugarcane, particularly ratoon sugarcane. So that was found to increase the not only crop yields but saved the water, saved the fertilizers, and improved the carbon sequestration rate in the soils, also carbon retention efficiency, etc. And of course, this is one of the important organic farming also. Organic farming, of course, if we see meta-analysis, organic farming improved us almost all properties of the soil, but except there was a slight reduction in the yield. If we see if we see the papers wherever that meta-analysis has been done, but there is actually depending upon our purpose. If you want to, suppose in initial years, if you want to forego some of the yield of the crop yields, but otherwise we can that can improve all the sustainable soil properties of the sustainable soil properties, whichever I have shown in the table. But here only sometimes we may get less yields for few years because of the low fertility and other things. But otherwise, it definitely improves the soil properties. And acid soils also, all of you know, earlier I have shown, acid soils actually, if we reclaim completely acid soil, means the bringing the soil, which is having the 5.5 or the below 5.5 pH to neutral pH, it needs a lot of liming material. So it may it may be very costly or expensive to the farmers. So what we did, our earlier scientists like the A.K. Sarkar or the P.D. Sharma ji, our farmer ADG, they worked under the network project. The output of that network project was that instead of going for complete reclamation of the acid soils, if we go for the amelioration type of thing, means if we applied 3 to 4, 5 quintals of the liming material, along with the this balanced nutrient management, like that whatever the soils are deficient in nutrients, all nutrients should be applied at recommended rates along with the minimum amount of the lime. And lime also application to the furrows rather than the broadcasting. That type of, and along with the tolerant variety. If we put together this as a package onto the farmer's fields, it will be the less expensive or the cost effective, and that also manages the acidity, nutrients, and will give the good yields to the farmers. Actually, this is the one of the technology that is developed by ICAR. And of course, tank center application particularly found very useful in red soil areas. Of course, this it should not be recommended to the wet soils and other type of the soils, because normally most of the cases this tank silt will have a little bit higher pH. When high pH is there, but it is a very good material for the our red soil areas, particularly in South India. And of course, one of the example from the Bangladesh also, where they are having the soils, they are facing two problems together. That is the shallow saline groundwater, shallow soils, and saline groundwater, waterlogging, and soil salinity. And for managing this, the farmers, they were taking only the crop, rice crop, and rabi crops they were not able to take because of the this shallow and the water availability problems. So technology, what they combined, two technologies they combined, that is the shallow drains plus straw mulch in Kharif rice sunflower system. Because of this reason, actually, earlier, of course, without this technology, they were getting the good rice yields, but sunflower was not possible. But with the combination of the shallow drains plus straw mulch technology in this system, they could take sunflower also successfully. Actually, there also improvement in the yield by sunflower from 70 to 200%, almost more than double. So this type of the technology is also combination of technology we should use whenever the multiple stresses are there. And from conclusion, actually, only thing is there are no dearth of the technologies in ICAR, agriculture universities, NGOs, and also KVKs. We have developed so many technologies, climate resilient varieties for each and every crop. We are having the many number of varieties. And also technologies have been also developed. Soil management technologies are there, nutrient management technologies are there, soil and water conservation technologies are there. But only what is lacking is that we are not using them depending upon the multiple stresses being faced by the particular ecosystem or the cropping system. We should select a crop variety first. Then we should use the combination of these technologies and putting them into a capsule form. That I am calling the multiple stress alleviate capsules. Means location specific, production system specific, multiple stress alleviate capsules, which including the tolerant crop or the varieties, along with the other practices needed. See, if we put them together in the form of the capsules, and these capsules, if we link with the aquatic stress maps, so that can be implemented by the farmers or adapted farmers easily, and their whatever the expected yields may come. Actually, this is the one point. Second point, already I highlighted that the hybrid modeling. Actually, we should go for hybrid modeling for a prediction of the yields or the impact of different stresses on the crop yields in future under multiple stress conditions. That is one. And the detection and quantification of the multiple applied stress impacts on affected crops through spectral signatures on real-time basis. This is also one of the very much required research, because we have just started this. Whenever there is a damage is there because of the hailstorm or the high rainfall or the excessive rainfall or the floods, we are not able to actually detect or quantify the area on real-time basis, so that we can give our measures immediately to the farmers after the effect, or the compensation measures also can. That for that, of course, this work, then some of the projects are going on in Maharashtra, for example, CropSap project is going on, but still a lot of work need to be done in this aspect also. Those who are young scientists who are there hearing this, they may do this type of the work. Thank you very much.
डाउट क्लियरिंग सेशन। यदि किसी का कोई डाउट है तो वो 1 to 1 अनम्यूट करके सर से इससे रिलेटेड कोई भी बात पूछ सकते हैं, कोई भी क्वेश्चन कर सकते हैं। चैट बॉक्स भी ओपन है, चैट बॉक्स में भी आप अपनी क्वेरीज को लिख सकते हैं, जैसे भी पार्टिसिपेंट्स इंटरेस्टेड हों। 5 मिनट का डाउट क्लियरिंग सेशन है। एक एक चीज को बड़ा अच्छी तरीके से सर ने बताया, उसमें मुझे नहीं लगता कि बहुत ज्यादा डाउट होगा। पीपीटी बहुत सेल्फ एक्सप्लेनेटरी थी और काफी वर्निंग इश्यूज को उन्होंने बताया है।
Sir, good evening, sir.
Good evening.
This is Dr. Neeraja Paspaleti, Department of Botany, Cluster University, Kurnool, sir.
Yeah.
Sir, excellent presentation regarding the sustainable agriculture. My doubt is regarding the alkaline soils.
Yeah.
So suppose if farmers come across the alkaline soils, so how to correct the pH and get the suitable crops for that?
Crops, that depends upon the crops. So many crops are there, but in the region, like the cotton is one of the crop. That is tolerant. Particularly Kurnool you are talking. Kurnool, of
Yes,
course,
sir.
already
Yes, sir.
cotton is there, I think, there. No? Of course, depending upon the what is called that is alkalinity, degree of alkalinity. Better to go for the first is the crop, then if possible, if the higher degree of alkalinity is there, we should go for the gypsum application like that. Gypsum application is recommended.
Thank you, sir. Thank you, sir. Thank you so much.
How simple is that manure application also in long-term fertilizer experiments is proven that organic manure applications also helps in reclamation of amelioration of acidity as well as alkalinity. That is the beauty of the actually organic manures, even green manures type of things. That also, if farmers sometimes may found gypsum very costly, they may just go for this type of the organic manures or the green manures also.
Okay, sir. Okay, sir.
Any other? Yes, is there any organic reclamation? Definitely, where are actually you go through this long-term fertilizer experiments data conducted on acid soils as well as the slightly alkaline soils. They are actually helpful in amelioration of the acid soils also. Even alkaline soils, of course, we recommend organic manures. There is no doubt. And what is the most preferred root type? Is standard one or the top foraging one? Actually, I feel that we should, if we have the both combination, it is better. Top foraging plus deep root system. Idiotypes actually we need to develop. What is the main function of the organic fertilizer? Organic fertilizer actually it not only improves and supplies the nutrients, but also increases the organic matter content of the soil, as well as some of the physical properties of soil. That is very, very important, because fertilizers, if we apply, no doubt they supply the deficient nutrients, but physical improvement of the physical properties of soil is very, very important under the changing climate, because then only we can call that as a sustainable soil management practice. And please share how the chemical residue stress can affect the health on soil. Chemical residue. Which residue are talking? Maybe pesticide applications are like that. Or the weed residue, that I don't have much idea about the pesticide application or the weedicide application.
Sir, the role of application of biochar to the soil in connection with the stress, physiological stress.
Yes, actually, particularly when we were there, I was there at a CREDA, we used to conduct that experiments, biochar application to the particularly red soils, okay? That we used to found it increase, yields anyhow increase will be there. Different types of biochars we tried, that the biochars prepared from the red gram, that is our red gram stalks, or the cotton stubbles, as well as the even agroforestry waste like that. All we found that improves the, no doubt, organic carbon content as well as the soil moisture holding capacity also. But over the period of application of the 5-6 years, continuous application, we studied after 5 years, there was a good improvement in the soil properties, physical properties particularly. Particular only thing is that biochar preparation, it is a very, very important. For that also, actually, CREDA has developed one small kiln for the small farmers where wants they can purchase also 2,500, 3,000 rupees one that maker costs.
Good evening, sir. Myself, Srirada Burla, sir. Visakhapatnam KVK.
Yeah.
Sir, what is the quantity for the biochar, sir, for 1 acre?
We applied around, two types of experiments conducted at CREDA. One is the large quantity of biochar applied, that is the 6 tons per hectare applied, and then residual effects studied for the 5 years. Okay. But initial year we applied first year higher quantity and then studied. And other type of other experiment is also there where around 2 to 4 quintals per hectare. This is applied.
2 to 4 quintals per hectare.
Yeah, tons, I think, sir. Tons, 2 to 3 tons.
Tons, sir. Yes,
tons per hectare applied and studied every year, alternate years we applied actually. One is the 6 tons per hectare initial year, then studied the effect, residual effects continuously without application. Other is the 2 to 3 tons per hectare every year, alternate years. In both cases, actually, there was an improvement in the soil physical properties as well as the yields of the maize as well as the red gram.
Thank you, sir.
Particularly in red soil, this only I am telling for the red soils, not for other soils. Okay.
Thank you, sir.
Nandini.
Yes, sir.
I think सारी queries resolve हो गई हैं.
हाँ जी सर, it's I think सारी हो गई हैं covered.
Conclude करिए आप.
Okay, sir. So thank you so much, sir, for this valuable session. And your presence truly makes the day 7 of Marti 2025 more meaningful, more graceful, and far more enriching for all of us. We are genuinely honored and blessed to have you with us. With utmost respect and with deep gratefulness, we are very much blessed for your presence here. Please be connected with us for any future related academic activities of AgriMeet Foundation Bharat. Once again, thank you so much, sir.
Thank you so much, Daksha.
Thank you. Okay. Thank you very much.
Okay. Namaskar. Jai Shri Ram. Good night.
Good night.